probably just saw the creative portion of my project, Blobjects, but I'm going to take you through how I came from my previous project to where I am now with Blobjects. This is Raymarching Revisited. First, I will begin with the end of the previous video, which was collisions and fractals. This was my goal based on the previous tutorials, and I decided to go ahead and do both. First, a refresh on what Raymarching is. The previous video, I really emphasized the Raymarching algorithm, but the truth is, it's both the sign distance field and the Raymarching algorithm that create Raymarching. The sign distance field is essentially just the definition of where all the shapes are in the scene for the Raymarching algorithm to be able to detect them with and visualize them. Ultimately, fractals are just doing the same thing a bunch of times, but this can be deceptively difficult, and that's reflection and repetition. Basically, you take a coordinate and literally change its coordinate evaluation, and it's ultimately the goal to represent as complex a figure as possible using as few evaluations as possible. And this is how you apply those principles to fractal generation. This is the Menger sponge. It's a famous fractal that is created by taking a square and then cutting out a bunch of squares around that square and doing that over and over and over. Basically, on the right, you can see the code that's used to make it. And you begin with your base square. And then you fold it using the methods I described in the previous slide about repeating and mirroring. And then you cut a hole. And the best way I can describe this is basically imagine folding a piece of paper a bunch of times, then punching a hole through it, and then you unfold it, and there's a bunch of holes even though you've only made one punch. Another example of a fractal is the Mandel bulb. I won't go super in-depth on this because I didn't end up using this for the final Blobjects project, but the reason I didn't is because, as you can see, their little edges aren't exact, and I think you could, if you try to do collisions on this, you might fall through random parts of it. Next, collisions, and it's a lot trickier than it sounds, because you might think, oh, we have the data of the Raymarch algorithm. We have the distance from every object in the scene, and that's true, but only on render image inside the GPU. So tragically, we are unable to access that data readily from the CPU because, for the most part, it's a one-way street between the CPU and the GPU. And I had a bunch of ideas on how to actually solve this problem. My first one was writing to a render texture and reading it off of the render texture onto the CPU. I'm not sure if this would work, but I did go fairly deep into this method, and I think it would work, but it would have its own host of issues. My other idea was using a compute shader, which is ultimately sending a bunch of packages of like instructions to the GPU, and then the GPU will basically offload compute from the CPU and be able to read it back at a moment's notice. But I honestly have never used compute shaders before, and I am really excited to learn. This felt like too much of a detour for this project. Now, my final idea was a parallel level of detail or LOD version to run on the CPU, which I am going to dub the Plod Verokpu method for the rest of this presentation. So using the Plod Verokpu method, essentially the CPU would also run all the same code the GPU does, but at a lower resolution. These two great videos I found during my research, I believe Code Parade has its own custom engine, so I wasn't really able to get a lot from that. But Plod Verokpu, it appears that Jelle used the Plod Verokpu method in his game, and I knew it was made in Unity, so that's really great, and I knew it was possible. So the Plod Verokpu implementation is fairly simple when it comes to the Raymarch algorithm. We essentially just write this same code in C#, and we only have to run it for as many points define the surface of whatever thing we're trying to calculate collisions for, instead of every single pixel on the screen, which is what the GPU does. Doing Plod Verokpu for sign distance fields is actually a lot harder because it's not as simple as just copying and pasting the code from the GPU, because that's HLSL, and that code is pretty different from C#. So even though you can copy paste it and then just replace all the float 3s with vector 3s, it still doesn't work because there's a whole library of code that we don't have access to in C#. So I had to write my own mini library. I'm sure there was a library accessible somewhere online, but I wanted to make sure that all the methods were exactly what I wanted and didn't have any weird other stuff going on. So I was like, went ahead and wrote all the helper methods myself, which was time consuming but worth it in the end. This is the final portion of the Plod Varokpu, and it's the best optimization you could possibly find because using the signed distance field, you're able to determine how close you are to objects and whether or not you even need to run the Raymarch algorithm. The difference between this and the GPU is obviously you always need to run it for the GPU because you can see really far into the distance. But with the CPU, you can imagine you don't really need eyes, so to speak, to collide with something really far away. You only need to see as far as you can collide with things. And that's all we need for collisions. Let's go. So we're able to have all the data, and then we can actually make collisions happen. So applying what I learned about fractals and about collisions, I decided to make the Blobjects game. But the first thing I did was create an infinite fractal domain of the Menger sponge. The next thing is you can make cool visuals by telling the GPU information about the game state, like the velocity, the direction the player is facing, where the blobs are in the world. And this is a little tricky because I also had to, for example, loop the coordinates using similar mirroring looping methods as I did on the GPU, but that wasn't super tricky to figure out. I was also able to make more optimizations to the Plod Varokpu method than the original, so I was able to do more iterations on the GPU, but I didn't actually have to do that on the CPU because my colliders would have no way of getting in there. They were too big, so I was able to make a more detailed render on the GPU. And also the spheres on the GPU where you collect have sign distant or have sign functions that like warp them and wiggle them a little bit, but I didn't need that on the CPU because they just needed to be spheres. The current bottleneck is the GPU, I think, actually, because the way I'm doing it is I'm sending all the transforms of all the objects that are floating around to the GPU, and then they're looping through each of those and rendering them to the screen, which isn't very efficient. But there's a cheat code for GPU optimization. You can just have less pixels on the screen. So if you want to play this at like 1000 FPS, you could just turn down the resolution really low, and it works just as well. However, this is sort of a cheat code. So in conclusion, I think it'd be awesome to use this with compute shaders, and ultimately I think that was the right way to do it if there was one that could make this project run even faster. Reading texture data from the GPU is another little interesting rabbit hole that I think could have some fun functionality. Then there's this idea of arbitrary object transforming. This is just something I made up, but I had this idea where for a GPU optimization, you could have an object in the location and then another object in the location that the CPU sends. But instead of just rendering both, you can render one and then calculate how to repeat space and warp the coordinate plane to replicate it in another way. I don't even know if this is possible, but it was just a fun idea I had. And then finally, there are some Blobject optimizations I could use, such as burst compiling, the GPU side Blobjects, and more. However, I think actually the burst compiling, I did experiment with that, but it didn't do as much as you might expect because, like I said, I think the bottleneck is actually on the GPU right now. But yeah, you can check out Blobjects on my itch, and I hope you guys have a great day. Peace.